Hello everyone, welcome back to ptet.chemistry channel. My name is Dr. Art. In this tutorial video, we'll go through this AQA Group 17 or Group 7 chemistry, which is basically the chemistry of the halogens as well as the associated compounds where they can exist as halide ions or halide salts. In this first question, chlorine is a very important industrial chemical. So chlorine exists as these diatomic molecules where you have 7 electrons in the outer shell. But then with 7 electrons in the outer shell, it's not going to be able to, stay as a stable atom without a fully filled outer shell. So on its own, with another non-metal atom, which is itself the chlorine, they will just share 1 electron and therefore giving you this diatomic molecule Cl2. Deduce the half equation for the oxidation. So we know about the acronym oil rig, where the oil basically means oxidation involved, or oxidation is loss of electrons. So from the chloride ion Cl minus to become Cl2. So the Cl minus lose electrons. So that is why we have the plus electrons on the right hand side, because it means from the left to the right, the Cl minus has lost the electrons. Balance the atom first is the most important thing in this kind of half equation. 2 chlorine on the left, so I put 2 Cl on the right, so I put 2 Cl on the left. So here I have 2 of these chloride, minus 1, twice of them, 2 of them, minus 1 give you minus 2, and therefore I need 2 electrons in order to balance the charge there. Next one, give the oxidation number of the manganese in these ions. So the overall charge of the ion is -1. This is the sum of the individual oxidation number. The manganese is what you want to find. Oxygen in a compound or bonded to something else, oxygen always has a -2 oxidation number. So having set up the -1 overall charge, that's the oxidation number of the ion equal to manganese plus 4 times the oxygen. Each of them is a -2 there, so that means the -1 plus 8 equal to manganese. This means that the manganese is a +7 and not just 7 but a +7 there. Therefore, deduce the half equation. You're in acidified solution, you have H plus, you're going to get manganese 2 ions, which is the Mn2 plus aqueous ion. This is the classic purple going to pale pink, or very, very colorless, as the color is very, very pale. And therefore it looks pretty much colorless. So what we have there is MnO4 minus plus H plus electrons, and this give you the Mn2 plus as well as H2O. We can balance our equation there. So 1 manganese, and we have 4 oxygen. So we'll have 4 H2O there because giving us 4 oxygen, 8 hydrogen. So I will have 8 H plus. And finally, all the atoms are balanced. Now we look at the charges. There is no charge on the water molecule. There is a +2 charge overall on the left hand side, courtesy of one of these Mn2 plus. So your target on the left to be +2 overall as well. -1 times 1 is -1. +1 times 8 is +8. So at the moment you have a -1, you have a +8. They add up to +7. +7 has to go to +2, therefore I need 5 electrons in order for the charges to balance there. In part B, chlorine behaves as an oxidizing agent. So oxidizing agent, it oxidizes the other substance, and what happened to itself? And itself will get reduced. So the way to remember the definition is it oxidizes other substance and itself get reduced. Now, if you know itself get reduced, only then you can think about the definition of reduction, which is gaining of electrons, as that was part of the oil rig acronym. And the rig there basically means reduction involved, or reduction is gain of electrons. So itself as oxidizing agent get reduced, itself gain electrons, itself decreases in oxidation number, etc., etc. Write the simplest ionic equation, which is year 9 or year 10 IGCSE A Level chemistry content. So chlorine is Cl2, bromide ion is Br minus, chlorine, bromine, iodine. So we know that the reactivity actually decreases down the group 7 from your IGCSE or GCSE or A Level chemistry. So therefore, the more reactive halogens on top there, they can kick out, they can displace the less reactive halogen at the bottom there. So Cl2 plus Br minus is going to give me Cl minus, and it will form Br2. So Cl2 can oxidize Br minus to become Br2 because Cl2 is a stronger oxidizing agent than Br2. When we compare oxidizing ability, we compare the halogen is to the halogen. Even though here we're reacting the halogen with the halide. Gotta balance your atom. So 2 chlorine on the left, so 2 chlorine on the right. 2 bromine on the right, so 2 bromine on the left. No charge, minus 1 times 2, overall is minus 2. No charge on the Br2, minus 1 times 2, minus 2. This one balanced atom, balanced charges is the simplest ionic equation. You can get that. Now give one observation that you will observe, that you will make. Well, Br2 there is definitely going to be much more intensely colored. As a liquid, it's a reddish brown liquid, but as a solution, they mention it about seawater. So that means that we are in aqueous solution because we are in seawater. So what we're going to get is not the pure liquid bromine color. So I will get like, you know, orange or yellow or orange yellow solution will form because that's the color of bromine water. Bromine dissolved with water, aqueous bromine there. Now in terms of electrons, that's the meaning of oxidizing agent. Again, as I mentioned, I would definitely go for the full definition first, which is oxidizes other substance, and then itself get reduced there. But they want specifically in terms of electrons. So after I say itself get reduced, therefore itself will gain electrons. So gaining of electron is reduction, as I did mention about the Ulrich acronym earlier. In part C, in sunlight, so chlorine can oxidize water slowly to form oxygen. Write an equation for this reaction. Part 1, give the oxidation state of the chlorine in the chlorine containing species that is formed. So Cl2 reacting with water. It can oxidize water to form oxygen. If you get O2, then what is the other product? Could it be HCl? Let me think about this. So you have 2 H2O because you want 2 oxygen on the left. Now I got 4 hydrogen. That doesn't quite make sense, does it? I think it's not HCl. I think it's HClO actually, because then I will get, if I have, let's say, 2 of that, then the oxygen will be, the oxygen is not balanced as well. Right question for this reaction. Did I mess up? Okay, let me just try HCl again. So, oh yeah, I should be able to balance the equation actually, because looking at the H2 and the CO2, that balance, but there's only 1 oxygen atom, so I could put a half in front there. So that does quite make sense. If you want, you can multiply by 2 on both sides, such that you get rid of the half, then you get 2, 2, 1, and 4, and your equation will still be balanced there. Now in the chlorine containing species is a HCl. We don't care about the number in front. So what we have is 0, which is 0 for the whole molecule. Hydrogen being +1 in the compound there. So each chlorine, when I move the -1 to the other side, sorry, +1 to the other side, become -1. So chlorine there is going to be -1. It's actually hydrogen chloride there. In part D, the last part of this question, this is asking you on why chlorine has a lower boiling point than bromine. We know at room temperature and pressure, that's 25 degrees Celsius. Chlorine is a pale green gas. Bromine is a reddish brown liquid. And then iodine is a gray-black solid. So what happened going down group 7 or group 17? Definitely the melting and boiling point increases. So I can say that both Cl2 and Br2 have simple covalent structure. So this is about structure and also bonding, as that was your AS key concept. So we break only weak intermolecular forces, but then these are elements, these are bonded to themselves, they have the same electronegativity, of which only your temporary dipoles, which is your London dispersion, temporary induced dipoles, or your London dispersion, or your van der Waals forces needs to be broken. So need to be overcome, need to be broken in order to melt or to boil. Well, that is the key concept there. Now you have to factor in what sort of things can affect your van der Waals forces. So Cl2 has, I can say Br2 actually. Br2 has stronger van der Waals forces, and this is due to two factors: stronger van der Waals than between Cl2, because number one, there is more electrons, more total number of electrons inside the Br2 than Cl2. But the second reason is Br2 has a much bigger surface area, as it has additional shell, and you have a bigger surface area than your chlorine molecule, and therefore your van der Waals forces get stronger, and therefore you will need more energy to break that. So I think these two are the key important factors, and that's the end of that 10 marks question there. In this question number 2, we have the distinguishing a pair of halogenated compounds, I think. Not really halogenated compound actually, not even halogenated. These are just normal alcohols. So butane 2-ols, if I draw skeletal formula, so skeletal formula there, 1, 2, 3, 4, butane 2-ol. So I'll put the OH at position 2 at carbon number 2. So there's the OH there. And now I have 3 carbon alcohol. So 1, 2, 3, like that, 1, 2, and 3. I have a OH at position 2. I have a methyl at position 2, so this is 2-methyl propane 2, all that. What else can I say? This is a secondary alcohol, and the reason I know it's secondary alcohol is because the carbon with the OH, the one I've bolded, the carbon with the OH is bonded to 1 and 2 other carbon, whereas this carbon here, the carbon with this OH is bonded to 1, 2, and 3 other carbons. This is called a tertiary alcohol. What is so significant about tertiary alcohol is there is no hydrogen on that carbon with the OH, which means if you don't have the hydrogen, you can't lose the hydrogen because you never have it in the first place. You cannot oxidize, cannot be oxidized. And that is why tertiary alcohols cannot be oxidized. So you gotta distinguish, you gotta have reagents that can distinguish them. So you're gonna heat with acidified, so H+, dichromate 6, Cr2O7, so there's Cr2O7 2- together with acidified solution. Here I'm just putting in the potassium ion, K+, you need 2 of them, K2Cr2O7. You need it to be acidified for the redox to work. So the secondary alcohol, so the butane 2-ol can be oxidized. So the secondary alcohol shows orange to green coloration. The orange color is the color of the dichromate 6, whereas the green color is the color of the chromium 3+ aqueous ions, as the chromium +6, which is orange in solution, it will go to chromium 3+, which is green in solution, and that is chromium +3 species there. But what is going to be the negative result? Whereas the 2-methyl propane 2-ol will have no color change. Shows no color change, which means it remains orange because the oxidizing agent cannot oxidize it there. So this one should be at the bottom there. The observations with the 2-methyl orange show no color change. It remains orange in solution because the oxidizing agent doesn't do anything to the tertiary alcohol, as you don't have hydrogen on that carbon with the OH to be lost, to be oxidized there. As for propane and propene, we have alkane and also alkene. So propane there, this is your CH3, CH2, CH3. This is your saturated molecules where you only contain carbon-carbon single bond. And then we're going to compare these to an alkene, whereas alkanes were saturated. Alkenes is what you call unsaturated because you have carbon-carbon double bond. Carbon form 4 covalent bond, so this is skeletal formula, I've shown 1, so there is 3 hydrogen there. Carbon form 4 covalent bond, there is 1, 2, and 3, so there's 1 hydrogen there. And this is the double bond, and carbon form 4 covalent bond, 1, 2, so there's 2 hydrogen at the end there. The classic test for alkenes, so you will add aqueous bromine, you will add bromine water. So what happened with the alkane is no color change, it remains orange. So no observable change. It remains orange. It's the same thing because orange yellow, that's the color of bromine solution. Whereas the observation with propene, this is carbon-carbon double bond. So yellow, orange bromine solution will be decolorized, or yellow, orange bromine water. There's bromine aqueous. There's Br2 aqueous. Gets decolorized or decolorizes. So basically it turns to colorless as it undergo addition reaction. The next bit of this question, this is using silver nitrate in aqueous conditions and aqueous sodium nitrate. So what can we do here? We have a silver ions and we have Na plus ions. We know all sodium salts are soluble. We also know that all nitrate salts are soluble. That's our preparation of salts back in IGCSE and A Level chemistry. So here what you can do is add some sodium chloride solution, and this is sodium chloride solution. It's a salt solution, or you can say NaCl aqueous. We have a silver ion, so we can think about the ionic equation. Aqueous ion from the nitrate, silver nitrate, chloride ion from the sodium chloride. You're gonna get AgCl, which is a solid. So what we get is we get a white precipitate. That is the formation of the silver chloride. That is the test for chloride ions as stated in the syllabus even since IGCSE and A Level chemistry. The next one with the sodium nitrate, you're just going to form sodium chloride anyway, so no observable change. It remains colorless, so no precipitation there, so it just remain colorless solution. So there's no solid, the solution remain colorless. So we're just writing out all the observation as we expect it to be there. The last part of this question, this is magnesium chloride versus barium chloride. So the only thing that is different there is Ba2 plus and Mg2 plus. Think about what you use Ba2 plus to test for. This one is test for sulfate ion, as stated in your qualitative analysis practical component there. So what I'm going to add is I should add some sodium sulfate solution, or I can add some potassium sulfate solution. We want to start from solution, and the reason is because with the magnesium chloride, it forms magnesium sulfate, so no observable change. You just get the colorless solution, so solution remain colorless, because magnesium sulfate is not really like insoluble. Think about your solubility rules of sulfate ions. So solution remain colorless. Whereas with the barium chloride, you have the Ba2 plus aqueous that can react with the sulfate ions, and they will precipitate out the barium sulfate. So all sulfates are soluble except for barium sulfate, except for calcium sulfate, except for lead-2 sulfate. Solubility rules of sulfate, salt preparation, A Level, IGCSE and GCSE level chemistry. That's it for that 12 marks question. I think there was just very little of the question that was actually on the halogen chemistry there. There was just a test for chloride. The rest of it seems to be miscellaneous stuff there. So yeah, that's the end of that 12 marks question. Alright, so I'll leave it there for these short tutorials, particularly on halogen chemistry, mainly in the first question earlier. There was a little bit of organic chemistry and test for ions, I guess, in the second question, which I just went through. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry. There's a ptet.chemistry on Instagram, Facebook, Twitter, Telegram to get connected, and do get in touch for highly personalized private tutoring for AQA, EDEXA, or any other exam bodies. Thank you for watching. I'll see you in the next tutorial video.